Hi, this is Chris Mognitsky with the Fort Worth Astronomical Society, and welcome to the International Observing the Moon Night. Sorry, got messed up there for a second. Um, Tonight we'll be looking at the moon. I have a number of telescopes set up in the backyard, and I'm here in the studio, which makes it much easier to do observing. I have air conditioning. I don't have to worry about bugs. Uh, I don't have to worry about street noises or anything else. It is nice and comfortable here. So without further ado, let's go ahead and start. Right off the bat, we're going to be using two telescopes. I actually had another telescope and I just have to swap it out. We'll be using a Celestron 11-inch Schmidt-Cassegrain at f10, and we'll be using a Raptor 61. It's a little small refractor. It's a very wide angle scope. I had another scope on there, an 8-inch Ritchie Cretan, but I had an issue with collimation and I was trying to focus. I could not get a good focus. Swap out the telescope is the solution. So without further ado, let's go ahead and start. Here we are. So the moon is almost full. This is a narrow field view. We are actually looking at, let's see, what are we looking at here? South to the north. I believe that's the way we have it set up. Let's see if we can do miscellaneous controls. Let's see. Can I flip it? Flip. What I'm trying to do is see where. There it goes. Flip. None. So we're going to see if we can flip it in the right direction. Is this the right direction? We may not need to. Let's go ahead and just not mess with the flipping. So we're at maximum zoom out. We can see some of it. If we can't recognize anything, I have, as I did at least. Uh-oh. Oh, that wasn't right. Chrome shut down. Oh yeah, let's not. Never mind. We don't need Chrome over there. We've got Chrome over here. So Google Earth, if you go, actually you go to moon.google.com, you can see a number of planets and moons that you can look at the surface of. So right now, let's see if I can get it just right. We're looking at Copernicus right there. So Copernicus should be somewhere right about there. This is the face of the moon that we're looking at. So I will drag this over here so I have a reference point. Okay, how are we looking? Okay, here we go. So this is Mare Serenitatis, the Sea of Serenity, and we have Sea of Tranquility right over here. And if I remember where everything is, there we go. Yeah, right about hereabouts, I believe, is where the Apollo landing was. Let's zoom in on that. And see, where is it? Where is it? Where is it? I am looking for, I'll show you what I'm looking for. I'm looking for two craters really close to each other. Then when we come over here, there we go. Sabine, Collins, Aldrin, Collins, and Armstrong. And the landing site was somewhere in this area. So what we're looking for is Ritter and Sabine. Let's zoom out just a little bit. And if you have any issues with hearing my audio, just please let me know. Just go ahead and put it in the chat, and I'll be able to deal with it. So, well, actually, let's get this orientation right. There is, here we go. So that's this. We're looking at over here. This crater right there and that ridge line right there is going to be the same as this crater here and this ridge line. So from here, we're looking across to there. Ooh, so I got some wind. So, right over here. So the Apollo 11 landing was right about there. Okay. I'm not liking how much wind there is. I have a little bit of motion as well. So let's drag this over. I have my controls here so I can move it to wherever I need it. All right, let's go ahead and look at the Terminator. So we're at 91% illumination right now. We're not seeing a full moon quite yet. That should be tomorrow. And we will see, well, we'll see what we can see today. So first of all, let's check out the settings. If there's anything weird. No, nothing weird. So I actually was doing some imaging a couple days ago, I believe on Thursday. One of the things about doing astrophotography is that you don't just take one image, you take multiple images. Multiple images. Every time you double the amount of images, you have the amount of noise. So with things like planets, things with the moon, things with the sun, or photos with the sun, we don't just take one picture. We will take sometimes dozens, sometimes hundreds, sometimes thousands. When I was doing the imaging on Thursday, I did think about 3,000 images, 3,600 roughly. I took the best 360 and I stacked them so I could get something better. And I actually have those on Astrobin. I'll bring those up in just a bit. But we are able to see a lot more detail when we stack than when we look at it this way. So I'm taking quick images. Let's see if we can, oh, for example, here we go. Looking at this crater, we can see the ejecta rays coming out. And if I look at my settings, 200 millisecond exposures with no gain. Okay, 200 milliseconds, it's not a quick exposure. I can go faster. Well, maybe not that fast. 30th of a second. Let's see what we can get. Check our histogram. Not getting very much at all, but you can see it's jumping quite a bit. So we got some wind. Not ideal. But it's not streaking as much as it was before. So what do we have to do? It's moving. Let's try this. Where'd it go? Where'd it go? Tools. Live stacking. So live stacking, oops, let's see, log back in. Live stacking is a technique where we do the stacking, but do it live. I have not been able to do this very well lately. I don't know why. So I want to see what is going on. Okay, let's fix this. There we go, that's a little bit better. So this stabilizes the image. We're able to see it a bit better. Yeah, that's going to be a bit better. And it takes one image and then stacks it on the other. And if it's too bad, it just throws it out. It throws out the bad ones, keeps the good ones, lowers the amount of noise, and then sharpens it up. So everything looks like it's okay. We're just getting the best of the images. We're kind of getting rid of, well, best 10% right there. Best 10%, we're getting rid of everything else. Stabilization, surface stabilizing. So we got good ones. We got some pretty good, decent ones right there. Okay. Well, while that's going, let's zoom in. Let's see what it looks like. There we go. That's significantly sharper. Maybe able to sharpen up a little bit with the focus, but it's not bad right now. if I then take this into, if I export this as a TIFF file and then I take it into Photoshop, I can actually do a lot more sharpening, but I don't have it on this machine. Let's zoom in a little bit more, 200%. There we go. That's pretty good. We're able to see some more detail through here. Not bad at all. All right, so what are we looking at? This crater, we got Plato and we got Copernicus here. The thing I don't like about observing this close to the full moon is you don't have a whole lot of contrast. You don't see shadows except closer over here to the terminator. But what we can see, and this is always very interesting, we think of the moon as having light patches and having dark patches, but the moon's actually colored. Here's a darker patch within the brighter basalt. If you look down, you see darker patches near lighter patches. Here's some darker patches as well. So by analyzing the light that comes off of the surface, we can actually orbit the moon and use reflected sunlight from the surface through a spectrometer and find out what the surface composition is. So in this case, we're looking at basalt, but it's a slightly different mineral composition. Right there, you can see here it's darker, here it's darker. In the middle, it's much lighter, and we have an ejecta ray coming from this crater. So let's see, where is... Okay, so that's Sea of Tranquility down here. We'll have to move it. All right, but let's do that later. Let's take a look at the whole disk, see what we have, what we can find. Okay, here we go. Here's Plato. Plato is a very shallow crater, but it is deep. It's large and shallow. What that means is something large hit it. It's a large asteroid, smashed in through the crust deep enough that the mantle material upwelled, filled in the basin, and now it's basically like a little mare, like the material here. Looks a little bit darker. Hard to tell, but it does look a bit darker. So what we're looking at is Plato. Let's see, where is it? There's Plato. So if we look at it on Google Earth, that is this. And we have Plato P, Plato F. No, wait, here's Bliss. Never mind. Here's Bliss, Plato P, probably right there. Past Bliss, we have a couple more craters. So I don't know if these Plato C, R, B, O, P, F, if all of these are actually related to the same impact. I don't know. That would be interesting to find out because we have more over here. We have some rills. I believe they're called rills. They're cracks. So look at it from our point of view. I can't rotate it. Not the right direction. But if we come in, we can see these high cliffs all around from the impact. And if you want to follow along, you can. Again, you can go to moon.google.com and you can see the same thing we're seeing. You can see the entire surface of the moon mapped out pretty well. So we have a number of small craters within Plato. We can't really see them with this one. I actually put the wrong camera on this scope. I have a higher resolution camera. It has a, well, it's not, it is a higher resolution camera. It has fewer megapixels, but the pixels are smaller, so I can pull out more details. The downside is it's a much smaller chip and so much smaller field of view. This one, I can get in a good chunk of the moon, a little bit more than half the moon at once, With that one, I get a small piece of the moon. So it's very finely detailed. It's just hard to see anything in it. So if you have any questions or comments, go ahead and put them in the chat. I am monitoring so I can see what's going on. If there are any audio issues, please let me know. For some reason, I'm not able to hear my own audio. I'm not sure why. Looks like it's going out, but okay, so this is still going. Good. All right. Let's take a look over here at the edge. What is this? Are we hitting a cloud? Yes, I hope not. Oh no, that's the edge of the moon. Okay. Is it? Or is that some weird... Oh, I wonder if that's a reflection. That could be an internal reflection with the filter. Yeah, that could easily be an internal reflection of it with the filter, because this should be the moon's edge, not somewhere out here. I put a filter on here in case we want to do some other imaging. Yeah, I think it's a ghosting. That's okay. We can still see some detail. If I do... There we go, that's brighter. Checking it out here. Yeah, that's a ghost image. It's from the filter. Guess I should have left the filter off, but figured we could do some other stuff other than just moon viewing. Okay, so we have Copernicus now. Copernicus is a very large crater. It's a relatively fresh crater. And the reason why we know that is because it's still bright. The moon doesn't have erosion like we have on Earth. There's no wind, there's no water, but there is solar wind. And particles off of the sun do slowly erode rocks on the surface of the moon, which is one reason why when we go to the moon, it will be much easier to build underground colonies and bases than it would be to build them on top. It's easier to build on top. It's much safer to build them below. So we can actually melt the regolith and turn it into concrete blocks to build with, cover up our structures with it, and that will decrease the amount of solar radiation at the surface that the astronauts have to deal with. So it takes a long time for that solar wind to darken the material. We can see older craters and younger craters. And we age them just by how bright they are. So the bright ones are younger, and the dark ones are older. Some bright ones right here in the sunlight. So let's take a closer look at Copernicus. I wonder also if the live view isn't working right. Let's go ahead and snap off the live view. Okay. And yeah, oops. Fix that. Where were we? We're looking at Copernicus. So back to auto. There we go. There's Copernicus, there's Plato. So we're going to zoom in yet again. Looking at Copernicus. So we have multiple ridges of collapsed crustal material. So whatever punched through here, it hit hard. Punched through, damaged the crust. Apparently didn't go all the way down to the mantle because we don't have an upwelling of magma from the mantle to create the basalt. But what we do have, we can see right there in the center is some rebound, a rebound mountain ridge. So when something impacts any body, and it's large enough to make a crater that's deep enough to melt the material, it all gets pushed out. It gets pushed out into a bowl shape. But that isn't sustainable. The rock is a liquid now. So when it comes back, it flows together and it makes a peak. And then it kind of freezes. And we call that a rebound mountain in the middle of these craters. So if we look at Google, Let's get out of Plato and go south of Plato to Copernicus. There. When we look inside, this is what we're seeing. This is actually twisted. If you angle this off, what is that, 30 degrees? Yeah. If you rotate 30 degrees clockwise, that's what we're looking at. So we can see rebound mountains here. Ooh, we had some wind. It was such a nice day. We didn't have any wind earlier, and now we do. Not happy about that. It was great. Last couple nights have been actually quite nice. It may settle down a bit, so we can wait, see what happens. Okay, and any questions you have, go ahead and put them in the chat, and I am monitoring. Do a bit. See, I don't really want to do a longer exposure. If I do a longer exposure, then I have to worry about the wind shaking it. So 1/30th of a second right now is fine. I'm getting enough. Yeah, 3.5 frames a second is all that I can manage on full 24 megapixel frames. If instead I bin it, as if I bin it. What binning does is it lets me combine pixels, and so I can actually get, I want to say more data. I can get more photons per pixel group, but I lose resolution. So for some things it's fine, for other things it's not. Yeah, I'm just getting a lot of wind. And it becomes a bit faster too. Here is Copernicus again, with a bunch of craters all around it. Let's go up towards the Terminator. I'm going to do this because it keeps moving around. So, let's see. It's never going to be, or rarely going to be, the button I want. I'm trying to center out the moon again. Let's think it again. Oh, wait. Let's get it right back to where it was, because I want it over here at the Terminator side. Okay. Zoom in again. Here we are. So we have a complex over here, number of craters. This is something I was looking at a couple of days ago when the Terminator line was right over here. So this looks like it's the edge of a crater, but it's a very old one, and these are cliffs on the edge. It's wind. It's definitely wind. All right, let's see what Google calls that, what the map of the moon is. So we're going up. Yeah, here we go. Sinus iridum. Yep. A little prominence Laplace right over here. Let's get this up. Yep. So we have Plato. We have some mountains right here. Montes Recti is right about here. This interesting mountain range right in the middle of the Mare. So this is 5 miles, so call it 5, 10, 15, 20, 25, 30, 35, 40. So about 40 miles across. 40, 50 miles right there. That's the size of that. So the features here aren't terribly large, but they're always interesting. Then off to the sinus iridium. We have 1, 2, 3 craters. 1, 2, 3. Is that what we're looking at? Hold on. That looks like it's right. Yeah. Okay. This crater, that's Bianchini. Then we have Sharp. Then we have Marian. All right, this is neat. I totally forgotten that Google had this. I knew they had Moon at one point, but they've added on quite a bit too, onto Google Maps. When we go out, here we go. Helicon, right there, and we have La Verriere here. Interesting. So what we're looking at again, it's this is a live view of the moon from a telescope I have out in the back. Let's see if you're interested in what that looks like. Let's see if I can find it. Well, there we are. So that is the telescope that we're looking at. The telescope in the back I had to actually take down, so that's not ideal, but I put another telescope on there. We'll just get that set up for wide field views. This is a Celestron Schmidt-Cassegrain 11-inch. This is the Edge HD, and I have a guide scope on top that lets me lock onto a star. Now that I think about it, I forgot to focus the guide scope because I haven't been using it. I was doing lunar imaging last couple of days, and I forgot to focus it. So hopefully it's in focus. If not, I don't have a focus motor for it, so I can't automatically do it. All right then, we'll see. Okay. So this is one scope that I have. We go all the way up. We can see the terminator line right there. And that crater, let's see what that crater is that we're looking at. This goes over. So here, that's Harpless is right here. So we're going past Harpless and we're looking at what? Gonna be kind of let's see if we can do this. All right, there we go. So we're looking here. Bianchini is right there. Make a line to Foucault right there. Harpalus there. And going past Harpalus is going to be Babbage. Ooh. So that we're looking at Pythagoras. Anaximander. So this is Anaximander here, and that could be Pythagoras. Let's see what it looks like on the edge. Yep, that looks like it's Pythagoras. Or that's Pythagoras. Ooh. That looks like it's Pythagoras. And the reason why I say that is, let's go take a look at what's in here. Babbage has got to be one of these up in front. It's not that big. But something really interesting, the reason why I say this is Pythagoras is because I'm looking through here, and this is all old stuff. And there's nothing over here. But Pythagoras has got these big rebound mountains. And I don't know if you can see, but I'm going to make this brighter. Do you see it now? I don't know if you see it. Nope. I'm going to blow this up right there. Let's do it. That point right there. That looks like it's the tip of the mountain in the middle of Pythagoras. Right there. Just that dot. We don't see these dots anywhere else. We don't see any other mountains. That looks like it's the far wall of Pythagoras here. And that one dot right there is the rebound mountain. I'm gonna get a better view. There we go. So the sun is just barely lighting up that peak. I think that's pretty cool. Is there anything you want to see that's interesting on the moon? I'm just watching the chat on the other laptop. So here we go, Pythagoras. I wonder if I can just do regular binning. Whoa. Yep. And I bet if we sit here all night watching that, that little mountain's going to get bigger and bigger and brighter as the sun rises on the moon. So for this crater, the bottom of the crater is still going to be in night for a while until the sun fully shines over it in, I don't know, maybe a day or more. But on the inside, it is being lit up by the sun hitting this far wall. So it's not a lot of light, but it's not pitch dark. There we are. Can zoom out a bit more. But that's what it takes. So when I had it a lot darker, it was a lot harder to see. But right here on the Terminator, we're able to pick out some more details. Let's see what else we can find. What is that guy right there? So we're Pythagoras. We're going south to the Mare. Have Markov? No, here we go. What are we looking at now? Copernicus, so we've got to be looking at the edge over here. Sometimes it's hard to pick out what we're looking at. This, there we go. That's this complex. Aristarchus and Herodotus. Okay. And then here we have a valley. Valley Shorteri. That's what we see right here. You can actually see it. So there's the cliff side on this side. There's the valley in between. We see that little notch. Zoom in on that notch. And let's see if I find it again. There we go. I'm overexposing quite a bit of it, so we can see what it is. Ah, there we go. So this is the cliff line right there. And the valley goes next to the cliff, and we can see that here. We have a cliff line, and then two craters. See if I can move it over. Smaller craters, kind of hard to see. There's something right there. Okay. And there's that little notch right there is apparently this. Apparently we have a bit of wind. So we have a little notch where it turns and it moves. In that direction to our left. Looks like it goes out a bit, but it fades too. So I don't believe these are water-based ones. The moon, if it had water, it was very, very briefly. I think, you know, I don't remember what these values are. I want to say they're volcanic, We also have rills that are cracks, just from the moon cooling down. Cracks formed in the crust, and we can see these fault lines. I just don't know what this valley is, what caused it. But we got it right there. It's quite a bit of detail. This is really neat. I'm happy I dug into this. So if I come in, let's fix this. There we go. Now we can see, yeah, it's going to be darker, but we can see the crater a bit better. Aristarchus and Herodotus right there. And there's that little, it looks like a little hill right there, casting a shadow down onto Herodotus, so the light is coming this direction from the sun. And then, there we go. And the valley, as it moves over, that little notch is that little notch right there. Then two craters apparently over here on that side of the cliff. There's so little light there, it's kind of hard to tell. Let's zoom all the way out again. Yep. It's just wind. It was nice yesterday. It was very nice yesterday, but probably the winds picked up. Okay, let's do this. While this is going, I'm going to do things. Check my phone if there are any messages. Don't see anything. Nope. All right. That looks pretty good. Okay. Nothing going on right now. I'm going to jump on the second computer. Yeah. There we go. Ah! Well, that would be a moon. How about I minimize that and change my thing to half a second, change my, I'll just blow it way out, but that's okay. Fine, I only knock down my gain quite a lot. And we have that, and I need to, I forgot to turn on the cooler. That's okay. Let's cool down the camera. So if I go back, let's see. If you use things like DSLRs and you're familiar with DSLRs, you will see that, yeah, here we go. Okay, you will see you'll be able to take images. So if you want to start off with astrophotography, it's really easy. You can do it with a regular camera. You can grab a kit lens, put it on a tripod, do long exposures, you can get star trails. Go out someplace dark. Don't do it from the city. There's way too much light pollution. Go out to a dark sky site away from city lights, point it north, open up your shutter for 30 seconds, wide open, and see what you get. You will get trailing of stars. If you want to do longer, you can do a minute, you can do 2 minutes. I don't recommend more than about 2 minutes exposure with a DSLR because they do heat up. That's one of the reasons why we went to astronomical cameras. This is an astronomical camera. It's from ZWO, and what this one does is it actually has a thermoelectric cooler right up against the chip. And the thermoelectric cooler, if you put in a DC current, depending on which direction, there's going to be a hot side and there's going to be a cold side. The hot side can get very hot, but the cold side can get really cold. On this one, the cold side can get 35 degrees Celsius lower than ambient. What that lets me do is cool down the chip to really well below freezing temperatures. In the winter, I've got it down to minus, think the coldest I got was about minus 45, about minus 45 Celsius. So it was very, very cold. The advantage of having cold is you're limiting the amount of infrared photons which are hitting your sensor. The less infrared photons hitting your sensor, the less noise you have. So our cooled cameras lessen the amount of noise. There's a fan back here that sucks in air, blows it over a heat sink, and this what do you call them? These ridges are part of the heat sink, and the warm air blows out here. This is a automatic focuser, or a electronic focuser, I should say, that lets me focus remotely, so I don't have to be out there cranking a knob. The mount is big enough to handle the scope, and it works. This is a scope I had to take down because my collimation was off. I'd really hoped that it was going to work today, but it was way off, and I thought I had it fixed, but apparently sitting around the collimation changed, so, or something with the focuser, something happened. I had to drop this down for a totally different scope. I don't remember a picture of it or not, but we're gonna do this. Let's get my exposure way down. 16, there we go. So this is the full moon, or nearly full moon, 91% moon. But we can't see anything because it is too overexposed. So a half-second exposure, way too much. Ah. So now we're down to what, 30th of a second, 60th of a second? Okay. Yeah, that's a good place to start. Good place to start. It's still, ugh. That's pretty out of focus, isn't it? All right, let's fix that. I don't know what direction we need to go, so I'm going to go with 10,000. And oh, that looks better. It's getting there. Prepare to hit stop. Once we get some details. There we go. Okay. So let's do a couple things. Here we go. Ah, that's why. Okay. So I actually have some 13. Let's do 8. No. That's what I want to see. So I do have some autofocus routines, but I've had some issues with them, and I'm not messing with them right now. We can get a pretty good focus just doing this. And you don't actually have to have a system like this to do your own astrophotography. Like I said, a DSLR. There we go. It's a simple DSLR. It's Canon, and this is an older one. This is a T6i. Yeah, T6i. My kid likes to use this one. So with a kit lens, this is actually a little bit better than a kit lens, but not a great lens. This is a 28 to 105 millimeter zoom. It does not have to be a fantastic lens. All you do is set this to bulb, or manual mode. You can set to manual, set it to bulb. If you use bulb, you need a cable release, which looks like one of these things. So the cable release will actually plug into it, and as long as the button is pressed, the shutter will be open. You can just do that. Leave it open. The shutter release will actually, the electronic one will actually tell you how long the shutter's been opened. Give it a minute, give it 2 minutes, see what kind of picture you get. Play with it. That's all that astrophotography is playing with it until you get it right, until it looks like what you want it to look like. So, what do we have? Well, let's get a better focus. This is close, but not quite. But the nice thing about this is we see the whole of the moon. And the orientation is actually not too bad. All right, zoom way in. Okay. Now, I don't think this is going to be as sharp as the other scope. So 14, positive, better, worse. Worse. Okay. Okay. Let's dial it in now. So with this one, the focusing is super fine. And this does have focusing routines. You can get it sharper, sharper. That's pretty sharp. I'll go a little bit sharper than that. There we go. Okay, one more. No, that was too much. Well, split the difference. That's going to be pretty sharp at 400x or 400 times. Yeah, there we go. Nearly full moon. So that's pretty. I think it's pretty. Okay. See, Bart here says he has a T6i. I like it. It's an older camera, but it's, I think, about 10 years old now. It still works. That's the neat thing about technology now is you can have older equipment and it's still good. It doesn't have to be absolutely top of the line stuff. Now, I do have some really nice cameras. I have one nice camera. I have another Canon, my 5DS. It is a 50 megapixel camera. It is I think it's about 12 or 13 years old now. It is not a new camera, but it takes very, very nice pictures. I am very happy with it. It is a full frame camera. I have done some astrophotography with it. I found that it's actually so good that it shows the flaws in almost any lens. So unless your lens is just absolutely perfect edge to edge, it will find the flaws. You will have if it has a little bit of curvature to it, you will see chroma and color as stars get kind of spread out up in the far corners. There we go, in the far corners. But in the middle, usually it's pretty good. This camera will find all the flaws, but it takes excellent landscapes, takes fantastic portraits. So it's a great camera, but I don't use it connected to a telescope because these cool down very nicely and get me really good images. So here we go. We have the moon, the whole moon. That's pretty good. Now, one of the cool things that I can do with this one, which I can't do with a with a DSLR, is this. So I can say, this is my region of interest. Let's grab that. This is actually kind of cool. So my region of interest. If I have an object that I just want to see, for example, if I'm doing planetary imaging, if I'm imaging Jupiter or Saturn, and all I want to see is this one planet in the middle of my whole field, well, this is all wasted space. This is all wasted data. I don't need any of that. So I can have a much smaller region of interest. And now I'm just getting data from that part of the chip, ignoring everything else. My frames per second went to 50 frames a second. I can't record all that to the drive. I don't think I can, at least. Not with this laptop. But it's only 13, I don't know if you can see, I think it's covered up. 1392 by 1370, so it's almost square, but not quite. But what it is, it's letting me get a lot more frames per second. I can now do my lucky imaging. This is the technique where we go ahead and if I want to get really good images, I need a lot of frames. So again, if I double my amount of exposures, I have my amount of noise. So if I take one picture, it's got a lot of noise. If I take two pictures, it's going to be half. If I take four, it'll be a quarter. Okay. If I take eight, it'll be an eighth, and so on, so on, so on. So if I can figure out a way to get hundreds of images and then get rid of everything but the best 10%, the best 5%. If I have 1,000 pictures and I take the best 2%, that's 20 images that I'm dealing with. So it's better to get fewer really, really good images than to get a lot of okay images when it comes to stacking. So if I'm doing my regular astrophotography, if I take 100 images during the night, I may keep 30, 40 of the best ones and toss out the rest. I don't need ones where the stars are elongated from wind. I don't need ones with a lot of satellite trails going through them. I just want the sharpest ones. I want the best ones. And when I stack those, I get better data. So in this case, I'm shooting at 50 frames a second for this. And I can actually do this. Let's do start capture. So let's see what it does. I'm going to call it full moon, or moon 183 MC. And then I'll do number of frames. I'll do 500 frames. Why not? Right? So it'll capture this into an SCR file, which is a type of video file. They're raw frames. None dropped. Cool. So I'm almost done. There we go. 10 seconds. 10 seconds, I got all the data I want. I got 500 frames, and then I can go in and process them. I'm not going to do that right now. But if I jump in here, so that was 1.8 gigs. 1.8 gigs in 10 seconds. So it's not bad. I can pull it out. I can deal with that. If I just keep the best 10%, I've got 50 frames that I can then stack and I can do something with. But if you go outside now, this is pretty much what you'll see. If you are in the US right now, I should say. North America, if you're in South America, it'll be flipped. So you will see the southern regions of the moon as up. That's just our orientation. So I don't know if you've had to deal with flat earthers in the past, but that's one of the proofs that we have that we do live on a globe, is if you go south of the equator, the moon appears to flip in the sky, or to be flipped. It's just our orientation. It's just our orientation on a globe. So in this image, we can really see the coloring differences in the mare. So we can see the Sea of Tranquility is a lot darker than the Sea of Serenity here. So it's different material. And then we have the Apollo 11 landing site right over here. Let's see if we can zoom in on the Sea of Tranquility. Here we go. There it is. There's Sabine right there. So the Apollo 11 landing site was right in this area here. We can check that. Let's see. Yep. So we're going to go here. We have the Sea of Tranquility. We have this little prominence there. Matches up to this. Right. Is that right? Let's double check. Okay. We have that little burst right there. Oops. So that's it right here. We go across, and then, oh wait, no. Going across, and then Where's Sabine? There it is. Okay, yeah. So we are... What am I looking at now? Now I got myself all confused. Okay. Let's get our bearings again. So I need to move this down. There we are. Okay. There. Now I see it. So back to here, we have this promontory here. So Sabine is... What am I? No. This is that promontory right there, because there's this bright crater, Censorinus. That's Censorinus right there. Okay. That's Censorinus. This promontory is this one here. That crater is there. Sabine and Ritter. So just past, going out from here, here is the Apollo 11 landing site. Right there. Okay, let's get the other scope. See what it's looking at. Here we go. Okay, same region. Zoom out. Okay, here we go. Right there. Yep, Ritter and Sabine. Ritter and Sabine. And Moltke. Moltke. Come on. Moltke, and then right over here. Let's see if we can fiddle with the focus just a little bit. With large telescopes, they heat up and cool down. Heat up in the day, cool down at night. And when they cool down, because they're made of metal, the metal contracts. If you have a long focal length, like a refractor, it's usually not very much that it changes over the course of a night, especially if you have a carbon fiber scope. But with these, because it's metal, because it's a folded design, tiny amounts of shrinkage, of contraction, change the focus a lot. So here's what we're going to do. 14, let's see. Let's go in one direction, see what happens. Is that sharper? It's hard to tell. You know, it's the old joke with the optometrist. Is it better like this or is it better like this? That's actually sharper. Okay. That looks... That does look sharper. Okay. So Moltke right there. We have this. So right over here. Right over here. That's the Apollo 11 landing site. I'm going to do this. We're going to do a tools. We're going to do... Yep. Oof. We're going to do some live stacking again. And let's see how much more detail we can pull out. So let's let it do its thing. It will go ahead and stack. And we'll see just how nice it is. So 17. It's only picking out the best. So if we look at stabilization, frame filtering, we're only getting the best. The ones that are pretty okay, and the bad ones we're just tossing out. We're just only keeping the best ones. That's why our stack length is only 25. So I want to do 100 for the stack. Okay, and keep getting logged out of the laptop. Okay. Right. Yeah, I can't really rotate the image that we have here. That's just not really feasible. I would have to actually go out and physically rotate the camera, and I'm not gonna around there. And if I rotate the camera, then I will probably also mess up with the focus. But that's what I need to remember. We have Ritter and Sabine, so we look for Ritter and Sabine, and then just past that crater, Moltke, is the Apollo 11 landing site. Now, I have gotten a really good image of it before, but it is with the other camera lens. With the other camera on this scope. And it's a very, very narrow field of view. It's kind of a pain to deal with. I did a very large, let's see, where is it? Let's see if I can find it. I did a version of it a couple years back. I actually have a 900 megapixel version of it, but it is so large that I can't really put it in a place where everyone can see it. So I'm looking for, I'm looking for if I have it somewhere really obvious, and I don't remember where to put it. I'll have to, I'm just digging for it right now. That may be it. No, that's, here we go. Okay, so this is an image I took. Let's get rid of that. This is an image I took with the other camera and this telescope a little while ago. So if we look at it, here is Moltke. That's right there. There is Ritter and Sabine, and you can see just how much more detail I was able to pull out with smaller pixels and a better night of imaging and a lot of processing. But if we go here, here's Moltke. So right over here is the landing site. And yeah. So that's the edge of Moltke. And that little, I don't know what you call it. There's a prominence right there. So this is a little indentation. So yeah, I was able to image it really, really nicely, but it just took a lot of effort to do. And I don't think the conditions tonight are that great just because of the wind. And you can see we have some really, really bad frames that are just dropping, and we're only keeping the good ones. So it's been several minutes, and we haven't even gotten to 100 frames that are stacked. But we can always zoom out. Yeah, see, it's just jumping back and forth. There's a lot of wind. So, okay. If you have any questions or comments, go ahead and put them in the chat and I will see them. Yeah, I'm glad I put the other scope on. It's much smaller. This one is so big, it's basically a sail in the wind. And again, everything's set up on it just fine. It's just windy outside. So let's do this. The moon is interesting and all. It is International Observe the Moon Night. But there's other stuff we can be looking at too. Oh, Tycho. Look at Tycho. So I'm going to, let's change this to how much? 30 seconds? No, it'd be too dark. Okay. Yeah, we'll leave it at that. Okay, we have Tycho. So if you have seen 2001: A Space Odyssey, then you know what's down in Tycho. So let's see. Let's see who remembers their science fiction, their Arthur C. Clarke, and can tell me what was found in Tycho, which I think I just gave it away. Tycho is a relatively young crater, and you can see there is a rebound mountain in the middle, so it was large enough to melt the material and then have it flow out, come back into a mountain, and then freeze. It is fairly young, and we can tell because it is bright, so the underlying material has been exposed. We know it's young because of the ejecta. So all the material that's been thrown out from Tycho, and you can see it's gone, quite a ways. Hundreds and hundreds of miles is how far the ejecta got thrown out. And we know that at the time when this happened, that the moon did not have an atmosphere because there's straight lines going out. So it's a plume of material that was thrown out in one direction. Each particle made a nice perfect parabola and then fell down and made those lines. So these are ejecta lines. It's not just a rock that's being thrown out and lands. It is a large conglomeration of material from one location that gets pushed out. Some of it goes further because it's smaller. Some of it doesn't go as far out because it's bigger. It can have different energies depending on where it was. There's so many factors to it, but think of it like tossing out a dirt clod. When you toss out a dirt clod that's barely holding itself together, and it breaks up in the air, it's not all going to fall in one place. It will then start to spread out and land. But again, it'll do it in a line, unless there's wind. There's no wind on the moon, so we have these ejecta lines. And these do erode. So after a period of time, and actually you can tell here, if you look at Copernicus, the ejecta lines in Copernicus and the ejecta lines from Tycho, they are different. Copernicus is an older crater, so its ejecta lines have been darkened by sunlight, by solar radiation, but the ones from Tycho have not. And no, I don't remember the ages of the craters. I think we do have estimates on how old they are, but I don't remember any specifics. The moon is not my specialty, but I do know some observers focus only on the moon. I met a gentleman, it's been probably 20 years. He had several telescopes, but the only thing he ever observed was the moon. He didn't care about anything else in the sky. He didn't really look at the planets. Every once in a while, it's like, okay, yeah, there's Jupiter, there's Saturn, that's fine. All he really focused on, all he cared about was the moon. So that's what he did. When the moon was out, he was out there with his scope and he was observing and he was drawing, because this is a time before cameras were easily accessible, especially electronic cameras. And doing film photography was, it was difficult at the time. Film photography for astronomers was not the easiest thing. If you want to find out, if you want to dig deep, look up hypering film. It's a process of using nitrogen gas to nitrogen, I think argon as well. It's been a while. You would put your film in an airtight container. You would pump in like nitrogen gas under pressure, and it would push out the oxygen in the film, because you let it out as well, and then you it would make it more sensitive to light, or to certain wavelengths of light, I should say. And then you take that film in your dark room, you load it back onto the spool, onto your canister, and then you go out and you take pictures, and you have to use this thing within, I think, like a couple of days. So you would put in the canister, seal up the canister, and you would put that in your freezer, and then you would keep it in a cooler until you need it. You take it out, you take all your pictures for the night, and put it back in the cooler, and then you go take it for processing. Oh, excuse me. We've got wind. Okay, I don't see anyone has mentioned anything about Tycho. So in 2001, A Space Odyssey, the first monolith was found on Tycho. It was called the TMA-1, Tycho Magnetic Anomaly 1. Then they found one in, where was it? In Kenya. Was it in Kenya? It was found in the Rift Valley, and they called it TMA-2, even though it wasn't found on the moon. It was not found on Tycho, but it was a monolith. So, yeah. So that's one reason why Tycho is kind of famous. And I thought that was just interesting. I thought I'd throw that out. So we're looking at Tycho. We're looking at the mare in the area. Let's see. Let's jump over here. All right. So we're going to go down to Tycho. There is Copernicus. Where's Tycho? Where's Tycho? Hang on, let's get this thing. Okay, here we go. There's Tycho. So we can see a rebound mountain right there in the middle. Cool. And when we zoom in on here, go this way and that way. There we go. There's Tycho. Man, it's just jumping around, isn't it? Here is Tycho as well. Really not happy about how this looks right now. It was so nice the last couple of days. But that is one way you can tell that we are definitely not faking. Uh-oh. There we go. I think it dropped for a second. Oops. Okay, looks like we reconnected. That was weird and interesting, but okay. Managed to reconnect. Cool. Flat earthers like to use something called a P9000 P1000, P900. They're these Panasonic, they call it super zoom cameras. They have really small sensors, and the lenses are, let's just say that the advertised focal length is not possible for that aperture, not possible for that sensor with that camera lens. The way we typically do it, it's called the Dawes limit. Basically, it describes the maximum allowable or the maximum resolution for a given lens system. And the easiest way to think about it is you get 50 times magnification per inch of aperture. So if you have that's your maximum, theoretical maximum for perfect optics. I mean, they have to be perfect optics. No optics are going to be perfect. You can get close, you're not going to get perfect optics. Ooh, that's wind. So if you have you never do it by the focal length, you always do it by aperture. The focal length doesn't really matter. So if you have a pair of 50 millimeter binoculars, 1 inch is 26.5 millimeters. So it's approximately 2 inches at 50 millimeters. So that's approximately 100x magnification for perfect optics. But because they're not, typically for 50 millimeter binoculars, it's going to be 10x to 12x is going to be the maximum. So having 100x with a pair of binoculars is not feasible because they're not perfect. Having 200x with binoculars, that's never going to work. You're just going to, everything's going to be blurry. It'll just be bigger and blurrier. So with this, I can get really, really high magnification, but it's kind of useless for me. you can see when I zoom in, and again, I'm not calculating what my magnification is with this. It's still blurry. It's not really getting any better, and part of it is the atmosphere. The atmosphere itself isn't that stable. Yeah, I can get a little bit better. So as the night is cooling, I have to keep changing my focus, getting a little bit better, a little bit more detail. And back to Copernicus. I want to go to these edges here, to the terminator line, so we can see some more over here. I want to blow this out. Yeah. Let's light up the edge so we can see some more craters here. What are we looking at? Geez, I'm not even sure. Clavius. No, Clavius is to the south. And again, from 2001, Clavius is where the main bases was on the moon. That's when we go to the south, lunar south. There's Clavius. Clavius is really easy to find. That guy right there, that is Clavius. Basically, you go Tycho and you go south. Clavius is really easy to find. I believe that's Clavius. Is it? I thought it was Clavius. Unless there's another one. Hang on. Wait. Tycho. This is Clavius? This is Clavius. Okay. That's Clavius. This is Porter. It's so hard to tell. Because I can see these two craters look right, and there's Porter right there. Come on. I hope it isn't the squirrel who's jumped on my telescope. I'm hoping it's just the wind. I guess that is Clavius. It just doesn't seem right. Because here's Tycho. Tycho, Magnus, Clavius. Okay, let's do, well, it'll be almost a line. So here we go. No, line, Tycho. I guess that's supposed to be Clavius. Huh. Could have sworn it wasn't. Okay, all right. Well, I'm just fine being wrong sometimes. We all learn. Okay, cool. What next? What can we look at? Looking at the face of the whole thing. Let's see. Actually, I want to jump to something else. I gotta figure out what do we want to look at. Actually, there's a comet. I don't know how well we can see it today. One of the problems with having a nearly full moon is that it just lights up the entire sky. What we're going to be looking at, any other thing that we're going to be looking at is going to be something like a globular clusters. We can do globulars. We can do maybe some nebula. I have to find something, but the dim stuff, it's going to be hard to see. Galaxies are going to be really hard to see. Where's the moon? Ooh, Neptune and Saturn. Hey, let's do that. Saturn, Neptune. Should be able to see both. That's not what I want. There we go. Okay. So we're going to go to slew. No, not sync to target. Slew. Okay, solar system. We're going to look at Saturn first. Let's see what Saturn looks like. I haven't seen Saturn in a while. Confirm the slew. Okay. Should be close. I don't see it. I got nothing. Because our exposure is too short. Let's get a longer exposure. The only thing I'm worried about is, okay. Got nothing. All right, let's do this. Because I don't know what I'm looking at. So I'm going to increase the gain. Yeah. I can't tell what we're looking at. Uh-oh. I just can't tell what we're looking at. So over here, we've got the full moon, but I'm going to go ahead and take this thing way out again. 49, 48 frames a second. We go in 40, 20, 18, 12. Okay, so that was the difference. We did a region of interest that was just centered across the moon, and we had 50 frames a second. We went ahead and now we're using the whole chip, and we're down to 12.6 frames a second. So, okay. Any questions, comments, go ahead and put them in the chat, and I'll be watching for them. In the meantime, let's jump to Saturn on here. I just want to see what's, whoops, Saturn, confirm the slew. And I'm going to have to take a longer exposure because Saturn is a lot dimmer. There we go. So let's go. There we go. Okay. So I'm going to select a much smaller region of interest. Oh, no. No, 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 no. Too small. Let's get bigger. There we go. Okay. I can actually grab it like this. Move it over. There we go. Okay. So there's Saturn. And I can make an even smaller region of interest. Oops. Let's get it roughly centered. We got some rings. I'm going to drop my gain way down and zoom in even more. Oh, zoom a lot then. And yeah, it's not much, but you can see the rings are edge on. I'm going to fix this. There we go. So that looks like we have some moons of Saturn as well. I wish. Well, let's do that. Okay, so 1/4 of a second exposure. I'm going to double this. No, I'm going to do more. I'm going to do 1 second exposures. I want to see if we can see some of these moons pop out. And then the gain, can bring it way up. Okay, cool. We got 1, 2, 3. Oops. say 3 moons of Saturn that we've got. Okay. I've got it on my phone here, so if I zoom in, oh, cool, yeah. Dione is actually crossing the face of Saturn, but we're not going to be able to see it with this scope. But I definitely see that would be Titan. Below it is Rhea. And out over here would be Tethys. So Titan, Rhea, and Tethys on Saturn. Okay. All right. Let's jump to the other scope. Let's see if it calmed down. I'm not sure what's going on with this one. So I'm gonna, oh no. I hope. It's locked up. Let's see. Okay, I'm still able to ping it. That works. I'm going to drop it. I'm going to try to reconnect. Let's see. Nope, no, not that one. What I'm actually doing is I have 2 laptops out there outside connected to the telescopes, and I am doing a remote desktop connection to those laptops so I can control them. I can do everything that I need to up here in my office. Oh no. Okay. Yeah, I see the problem. So the problem is the imaging application on there has decided that it is it's going to crash. So yeah, I'm going to have to kill it, and then we will just restart. I do not want to reboot the computer, because then I had an issue a couple days ago where I tried to reboot it and it shut down. So I had to go outside and fix it. Let's do this again. Okay, and once more with feeling. Here we go. Okay, now I can come in here and kill it. I know it's not ideal. It looks like it died. No. No, it did not. Let's bring it up again. Okay, well, that's going up. So we have Saturn, Titan, Rhea, and Tethys. So that's cool. I think I'm going to blow this out again. Well, because it looks like, no, Neptune's away. Yeah. I was wondering if Neptune is in the same field of view, and I don't think it is. Oops, that's not what I'm looking for. This is what I'm looking for. Auto. Yeah, I thought Neptune should be somewhere over here. I don't see it yet. So let's jump over and see. We're not going to be able to see much. Not with this scope. But that is fine. Neptune confirm slew. That will go over. In the meantime, I'll get this one ready. Okay, that's not what I want. That's fine. Okay, I don't know what's what. So I'm going to do plate solve. Hopefully, oh, cool. Let's resync then. So one of the cool features now that we have is automated plate solving. And a plate solve is when you take your image and you take those stars and you pass it through a program and it will tell you what you're pointed at. You have to give it a little bit of parameters. You have to say, it has to know where it kind of is supposed to be pointed at. And then it needs to know the focal length of your telescope so it can kind of figure out, am I looking at a really tiny field of view? Am I looking at a wide field of view? But once it has that, it will go ahead and figure out what you're pointed at. And then it will actually tell your mount, hey, you're pointed over here when you should be pointed over here. And then it'll match it back up. So right here in the middle now, that is Neptune. Zoom way in. And it will not be impressive, but that is Neptune. And if I do something neat like frequency wave, let's see how much this will clear up. Not that much. Yeah, not that much. Oh, get a bigger one. Yeah. Okay. I'm going to do another resync because I didn't have it in the right position, not where I wanted it to be. There we go. So, okay, offset of 0.2 degrees, fixed itself, and there we go. So now we have Neptune supposed to be in the middle. Should be moving it to the middle. Okay. And I'm actually looking at the other scope. Let's see, I'm going to do 2 seconds on the other one. And lots of gain. All right, I'm looking at the other. Let's see if this one can figure out what it's looking. Not enough stars detected. Please. Yeah. 2-second exposures. There's so much wind. There's so much wind with the other scope that it's not. All right. Let's leave that one aside. Okay. Not planets. Anyone have any suggestions? Excuse me. A wide field target away from the moon. Could look at Andromeda. Let's do Andromeda. So this is Messier 31. Actually, before we do that, before we jump over to there, I have something else. So long as we're on the topic of the moon. Let's jump back on the moon just for a bit. Oops. Okay, confirm the slew. There we go. Super bright, super overexposed. So drop that gain down to nothing. Fix this. That's still way too overexposed. Let's look at the histogram. Oh, that's much better. Okay, now that's still too much. Let's let it do its thing right there. Okay, I'm going to zoom in. We'll talk about the moon. So when we look at the moon, we see basalts and we have silicates. So basalts are the darker materials that comes up from the mantle. Think of it as lava. Think of it more like Hawaiian lava, where it's dark, it's thick. It is in Hawaii, it comes up from a hot spot down the middle of the ocean. In the mid-ocean ridges, in the Atlantic and Pacific mid-ocean ridges, it comes up from the mantle and is pushing the plates apart. So when we look at the mare here, we're looking at that type of a dark material. Even though these areas are darker than the areas here, it's still overall dark material. We have samples from the moon that aren't just from Apollo. In fact, I've got some right here. So if you've ever seen, if you've ever been to NASA, either in Florida or in Houston, they have very large pieces sorry, they have small pieces of moon rocks that are embedded within big plastic lucite blocks. The one in Houston, it's actually 2 blocks. There's 1 block below, and the little moon rock is embedded inside, and there's another one on top of it. So if you want to touch it, you have to put your hand inside, kind of bend your fingers, and then you can just barely rub it, and that's all you get. What's this? It's a moon rock. Right there. Let's see if I can get it closer and focus on it. There we go. Not a whole lot of light. But this is a moon rock. This is a meteorite, a lunar meteorite. Now, the neat thing is that I have a microscope. So let's take a look at what this looks like under the microscope. Ready? Here we go. That's it. This is a small piece of the moon. So this is Northwest Africa 11421. So if you just go online, you can just go to Google, type in NWA 11421. You will find the entry for it, which describes the meteorite, describes where it was found, roughly, and by who, and the composition. There's going to be some information on it. So this is one of my 2 samples of this particular lunar rock. And today I was actually down in the Southwestern Adventist University's Thomson Observatory during the day. We were doing the club had a number of scopes out there, including some, solar scopes. And I brought my meteorites down there to show the kids. So this was one of them. And I usually let kids handle them, so they can actually hold a piece of the moon in their hands. So what we're seeing here, we have some, this is actually, it's a, let's remember, it is a lunar feldspathic breccia. So it's an achondrite. It is not a, trying to find the word for it. This is a conglomerate. So it is a bunch of different rocks that have been cemented together over time. It is not sedimentary. It is a silicate. So this comes from the highlands of the moon. So if we go back to the moon here, all the bright areas, that's where this comes from. And this is similar to what the Apollo astronauts brought back with them. So that's one reason why we are able to tell that these are lunar meteorites. I'm trying to open a box. Is because we can actually compare them to what Apollo brought back. It says push, but I can't open it. I have another one. Oh, there we go, finally. So with this one, there we go. All right. So with this particular meteorite, let's go back. Okay. we can see some of the material, the lighter material here. This right there, that's actually a rust spot. So there was a little piece of iron, and just the reaction in the air to humidity in the air has rusted it out, because it is not just iron, it is a nickel iron. It's not stainless steel. So if you don't take care of your nickel iron meteorites, if you don't cover them with epoxy or oil them often, they can rust just from the air alone, from the humidity in the air. Now, there is a Chinese palisite. A palisite is a meteorite that has peridot crystals in it, olivine peridot crystals, and they're very, very pretty. It's a metal matrix with these little bitty yellowish orange crystals inside. But the problem with this one in China, and I can't remember which one it is, what it's called, but it has a lot of chlorine in the metal, and the chlorine reacts with water in the atmosphere and causes the iron to rust, and it rusts very, very quickly. And it's a relatively common palisite. It was a very large meteorite, and there are a lot of pieces, and it's fairly, well, with a good saw, you can slice thin slices so that the crystals are surrounded by the metal, by the iron, and so light from behind can shine through. So jewelers in China made a lot of little pendants out of it. But if you don't seal it properly, if you don't take care of it properly, you can buy it, think, oh, this is very lovely. You wear it a couple times, and then put it away in your jewelry box. And then come back 6 months later, and you have a pile of rust with some yellow crystals in it. It's just what happens. So here we have a little bit of rust. This is plagioclase and pyroxene. You see little bitty bits here, small little white clasts in this larger dark matrix. If we flip it over to the other side, you can see this is just one large clast, one large piece here. And this dark matrix is holding all of it together. So we call this a breccia. It's a conglomerate of a bunch of other pieces. So I'm using a lens cap from one of the cameras as a catch for it. I have another one. So this is an end piece. And again, you can see this dark matrix, and it's just kind of all stuck together. And lots of different types of pieces. These are actually orange in this one. It's not rust. That's just the color of the material. And no, I have not analyzed the color of this material. But this was verified to be a lunar meteorite. So I can get, this may not be pretty. There we go. This is the polished side. Trying to get it not to reflect the light. So it's got little cracks through it. What this means is that it was shocked. So how did a moon rock get to the Earth? Didn't hitch a ride. It made its own way. And if you take a rock on the moon and you just pick it up and throw it, it's going to fall back. But if you take a really big rock and smash it into the moon at high speeds, you can knock off a bunch of other rocks. So if we're looking back at the moon, let's see, there we go. So we're looking back at the moon. We're looking at Tycho, okay? Big crater. Ejecta lines, right? Okay. Not all the ejecta, not all the stuff that was thrown out from the crater went back to the moon. Most of it did, not all of it. The stuff that did not go back to the moon went out. If it had enough energy, it was thrown out into lunar orbit or beyond. Now, the problem with lunar orbits is you have to be really close. to be within the moon's region of influence. If you get outside of that region of influence, if there's enough energy to push it at escape velocity from the moon, it will be captured probably by the Earth if it goes in the right direction. So stuff was thrown out from the moon, went around and around and around. Could have been thousands of years, tens of thousands of years that it orbited between the Earth and the moon, and at one point might have been slingshotted around the moon and then landed on Earth, crashed in the Sahara, actually in near Algeria, well, in Algeria, southern Algeria. So the neat thing about meteorites, let's see, what do I have? Ah, there we go. Hang on. I always keep a meteorite close by. Maybe not always, but let's see. There we go. Okay. Meteorite. So switch it to here. I wish I had the other camera set up, but I don't. So this is a meteorite. Let's focus on this. There we go. So this is a unclassified Northwest Africa meteorite. It's dark. You can see this has it's called a fusion crust. So the fusion crust is, this is the burnt outside of whatever is left. So this meteorite is 1/20th the size of whatever hit the atmosphere. And this one weighs about 280 grams, maybe about 287 grams. I just remember the weight. So this is uncut. This is just the way it fell. There's one side which is a little bit more matte. The other side was a bit more shiny. You can tell just a little bit right there. So this tumbled just a little bit as it came down. It actually came down more like this, tumbled a little bit, but it was mostly in one direction. And then it hit the ground. So this is what meteorites typically look like. They're just this dark color. Inside, it can look completely different. Let's get the other one. Here we are. Okay. I have the other parent piece. So this is what it can look like when it's cut and polished. And those shiny bits that you can see, those shiny bits are mostly nickel iron. And it makes this thing a little bit heavier. So this rock, if I flip it in the direction, these lines that you see, these cracks, this discoloration, this is at one point this was hit so hard that it cracked. And when it cracked, it made these, like, along the cracks, it was so hard that it melted and then re-solidified. And this one is cut. You can see at the very edge, it has some fusion crust. It's very dark, just along this outer edge here. There we go. But the inside is untouched, absolutely untouched. And I can show that off too on a different meteorite. So we'll go back to the lunar. Oops. There we go. We can look at this lunar one again, and we can see these cracks. This is the shock. We know what happened to this rock. It was hit so hard by something, another asteroid, or an asteroid that hit it so hard it knocked off pieces, but it shocked it. It cracked through these clasts. The clasts existed when this rock was on the moon. Okay, these pieces were together, they were solid, but the impact was so much that it put all these cracks through it. And then it went around and around and around and eventually landed on the Earth. This one does not really have any fusion crust. We're not really sure why. Every once in a while, we have meteorites like this. Usually it indicates that they hit the Earth very, very slow, or they hit the atmosphere very, very slowly. So they didn't lose a whole lot of, there wasn't a whole lot of energy for them to lose. And so they didn't get super, super hot. There's usually a little bit of fusion crust, not apparently on this piece. But really, really slow ones may not have that fusion crust. That's why this one's kind of a weird outlier. But the inside being nicely polished, you can see the clasts quite well. You can see the matrix material, and you can see the shock. So that's that one. Now the neat thing I always thought was neat is this. So this one is Northwest Africa 8327. It is a chondrite, and a chondrite means that it has chondrules in it. These circles, these little balls. Where it's rusty, that's nickel iron. Right there, that's some nickel iron that's not rusty, it's rather shiny. But all the red spots, this is rusting nickel iron. Let's see. And what's neat is that if you look, and I'll zoom in just a moment, but let's talk about the chondrules real fast. With the chondrules, this is the very first material that condensed out of the birth nebula of our solar system. So when it cooled down enough, this is this first material. So the planets, the sun, everything in the solar system, it has the same ratio of elements as all these chondrules. Now, some hydrogen and helium, but the metals, anything denser than or higher atomic number than hydrogen, helium, in astrophysics we call it a metal. So these chondrules here, all these little balls, if you look at them very, very carefully, they're untouched. So the how can I say, should focus better? There we go. So the fusion crust is only a few microns thick, and I can prove that by actually looking at it. So we have meteorite, we have the fusion crust on the back. So this is an end piece that has just been sliced and polished. You can see the fusion crust. You can see where some of the fusion crust cracked off. So looking over here and over here, the fusion crust just broke off. Let's look back on this end. You can see all those neat little chondrules. Now, we do something else with this. Guess it's not going to let me do that. That's fine. I'll go this way. All right. This is a very, very cheap, microscope, but it's not a very good one. All that shiny stuff, that is nickel iron. I'm going to go right to the edge. I don't know how easy that is to see, but I'm going to actually, let's change this. I'll put this down instead. With a white background, it'll be much easier to see. All right, here's what I'm doing. Okay, that's much easier to see. That is how thick the fusion crust is. It is so thin, just a few microns thick, that it cuts chondrules in half. And the half on the inside is unaffected. That means the heat from entry into the atmosphere never reaches inside of the meteorite. This thing was 20 times bigger when it hit the atmosphere. 95% of it was ablated away, and that ablation took away all the heat of passage through the atmosphere. So when this thing hit the ground, it wasn't like in Hollywood. It didn't make a big crater. There wasn't fire. There wasn't smoke and steam, and nothing was glowing green. This plopped on the ground, probably about 200 miles an hour. And then it frosted over. Why? Because the inside was still the temperature of space. The inside was still the temperature it was when it was going around in the solar system. So sub-zero, really cold, and it frosted over. And after a couple minutes, half an hour, it warmed up enough, probably in the sun or even at night, that the frost melted. But when it hit the ground, it was covered in frost. So don't listen to Hollywood for everything. So with this one, we can actually see that the chondrules, where'd it go? There it goes. My little Allen wrench pointer. Chondrules right here at the edge, there, that's cut in half. So the heat never goes inside. The heat never affected anything. It didn't melt anything on the inside. These chondrules, these little building blocks of the solar system, they're completely intact. So the chondrules clumped together and made bigger rocks. The bigger rocks clumped together to make meteoroids. The meteoroids clumped together to make asteroids. The asteroids clumped together to make planetesimals. The planetesimals collided into planetoids. The planetoids collided into planets. So everything grew from these little guys. So I think that was neat. And we can go on and do other stuff now. Let's see. So looking back at the moon, we have this. I'm going to check my other. Yeah, it's still windy. Try and look at Saturn. It's still trying to look at something. Yeah, it's still pretty windy. So turn it back on. Raw 16. Okay. Oops. Yeah, I'm not thrilled. I'm really not thrilled with that. And honestly, something's just not right. Okay. This guy. See what we're doing here. What else can we look at? Because I have a request. Did have a request. Okay, Andromeda. Let's go look at Andromeda. Let's see what we can find with Andromeda. Messier. Neat thing about this, Messier 31. Yep. And confirmed slew. Oh boy, okay. All right. Andromeda Galaxy. Should be somewhere over here. I don't think we're going to get a great image of it just because there's just so much moonlight right now. We're going to need a much longer exposure. Let's go to 4 seconds. Okay, I've got a really slow connection, which I should not have. There we go, 8 seconds. Increase my gain. And what I want to do is mess with my histogram. Okay, there we go. There's Andromeda Galaxy, right there. Kind of fuzzy. There's not a whole lot you can see. It's kind of noisy. Expected. In the meantime, let's tell this guy, can you please do another plate solve so we can center out Andromeda. Offset 227 degrees. Cool. It just moved it. It recentered it. Less effort. I don't have to keep hitting the arrow buttons to try to get it into place where I want it. it knows how much it's got to do it. So next thing we can do this. Oh yeah, deep sky annotation. This thing I like to do. So deep sky annotation. What this does is this tells me what am I looking at. So M32, M110, these are galaxies. So we're just looking at the core of Andromeda. This is not the whole galaxy. The whole galaxy spans probably about that much. Okay, NGC 0206, this is a, what's I'm looking for? This is a group of stars within Andromeda. If I want to do a better image, I'll have to do a longer exposure. So let's do that. Come on. So 8 seconds is not enough. Ideally, you know, let's do a 30-second one. 30 seconds is not a whole lot. I would, oh, yeah, if it wasn't for the moon, I would have been doing some other type of imaging with the other scope. Fortunately, yeah, I'm not real happy with that scope. I'm still not sure what's going on with it. Yeah, I'm not certain what's going on with it. It's not really running the way it should be running. Okay. The gain is way too high. Let's drop the gain down. And what dark? Minus 14 gain. 3 minutes. I don't want to do that one then. Flat? No. There we go. It's a little bit better. So we can see, again, this is the core of Andromeda. This is one galaxy here that's orbiting Andromeda. Here's another galaxy that's orbiting Andromeda. And the whole thing is spread out about that far or so. It'll take up most of the field of view. In order to really see it well, I really need dark skies. And this is not the place to do it. So what else is good? Do the veil. Double cluster. No, double cluster should be nice, actually. There we go. NGC 884. Let's do that. I think that'll be a little bit nicer. NGC, the new general catalog. NGC, and what was it? 88 double cluster is 884. Okay. So the double cluster is in Perseus. It is two open clusters, but one is closer to us, one is further back, but they have that apparent, they're close, they appear to be close to each other in the sky, when in reality they are not. Okay. I'm going to stop this 30-second one. Let's go 15 seconds. There we go. Double cluster. So two stars close to each other, or sorry, two open clusters of stars close to each other. Apparently close to each other. There we go. Yep. So they're just, excuse me. So something's up with my network. Yep. Not happy with how slow this is going. That is pretty slow. Well, it's 10:39 my time right now. Well, that's not great. Should be quite a bit faster than this. I have everything hardwired. I'm not going over Wi-Fi. Interesting. Okay. Let's do tools. Live stacking deep sky. Let's see if we can make it a little bit nicer. Let's see what happens if we tell it to go ahead and start stacking. Let's fix it then. Okay, we got some stars. So we're going to let this thing start exposing. Live stacking will just give us more data. It'll be a lot less noisy. Hopefully it'll look better. Find the frames. So we've got 2 frames already. Let's go 100%. There we go. Hey, that looks better. Now we can actually see some color in the stars. All right. That's much prettier. No, let's go back. Okay. All right, let's just let it do that. Take some more images. Look a little bit prettier. I don't know what's wrong with this other scope. It's like, I think it's just too much wind. And that's kind of sad because that's the big one. I could do more with it. I could zoom in. Yeah, I don't know. It's the first time I had to deal with this. So I've got this open in another window. Try it once more. Oh, excuse me, because I wanted to do some. I want to look at Saturn. I want to look at Neptune. See what else is in the sky. And Uranus. Neptune Uranus is just rising. It's still really low in the eastern sky. Pluto is not going to be feasible. The Milky Way is also way, way down in the southwest and is behind my house. That's not going to be feasible. But here, this one's not bad. So we can see the 2 clusters. So 1 and 2. Let's zoom out a bit more. There we go. So the double cluster. If you're looking at this through a telescope with a wide angle lens, it's like you just see a field of jewels in the field of view, or in the eyepiece. It's very, very pretty to get both of them there. There are thousands of stars in each one. We're not picking up very much just because there's a lot of light pollution in the city. It's a small aperture scope. We're doing imaging. There's still a lot of data, which is almost black. You can see it down in here. It's not black, but it's almost there. I'm using a special filter on this. It's better for nebula, but we can pick up the stars pretty decently as well. So we've got 12 stacked. We've gotten rid of a lot of the noise. It's starting to look pretty good. There, a little bit black. A little bit of blue to the background now. So stuff like this is visible. It's visible now, at least. Okay. Let's get this. I'm going to go. I'm still looking at the other screen, just so I can try to get some data. I still don't know what's going on here. On cooling. Yeah, it's still windy outside, so yeah, my scope is moving a lot more than I had hoped. So I don't know what else we can really do about it right now. I'm going to reconnect, see if this can do anything. Solving the frame. I'm trying to plate solve there. Yeah. Not enough stars. Try longer exposure. Once more, see what happens. Okay, what else is good? What else can we see with this one? The dumbbell. Actually, that's pretty high up. Dumbbell nebula. Let's do that. M27. All right. Let's check that out. So I can stop this. Got 19 frames. Yeah. So the double. And if I... Let's see if I can get this. Yeah. So you can see even more stars. A lot of very, very faint ones. Processing, we can actually pull out a lot of these really faint stars. So going down to the core. So we have two types of clusters. We call them open clusters or globulars. They're two different ones. An open cluster is a group of stars that are all born together from the same birth nebula, but they've moved out of it, or all the gas has not been used up, it's been blown away, so that just the group of stars are there. And they're typically spreading out. They don't stay together. Once they're born, they kind of just move apart. Just gravitational interactions throw them out from the nebula. And when we look at something like Pleiades, M45, when we look at it, we see some nebulosity. And we used to think that was the birth nebula, and actually turns out that with Messier 45, it just so happens that it's moving through a dusty region of the galaxy, and when it does, the light from the stars is just bouncing off that dust. But here, we don't really have any nebulosity. We just see the stars. And when you see the stars, you see all of them together, and they're different sizes. They're different types. Some of them are big, bright blue. Some of them are small. Some of them are like that guy, reddish, yellow, red, anywhere from white to blue. They're all sorts of sizes and all sorts of ages, but they all came from this same birth nebula roughly at the same time, or within a range of time. Now we have the globulars. The globulars are external to our galaxy. They actually orbit the Milky Way, and they also orbit other galaxies. We've been able to see globulars in Andromeda, in Triangulum, and in several ellipticals as well. Those are big balls of stars. In a open cluster, you may have hundreds to thousands of stars. Globulars are hundreds of thousands to millions of stars. Big difference. And they look like a big ball of stars, and they kind of fade out towards the edges. There are fewer and fewer. The reason why they're also old. They're about as old as the galaxy. So the reason why they kind of stay together in a ball is it's kind of like boiling water. When you boil water, you're adding energy to the system, but the steam that comes off of it, those are the molecules of water that have too much energy, and they leave. So you can't heat up the water in the pot higher than boiling point. Anything more energetic goes off. So the temperature of the water stays constant. All that excess energy goes to throwing off molecules of water as steam. In a globular cluster, the stars interact with each other. So they have a set amount of energy at the beginning, but through their gravitational interactions, some stars lose energy and fall in closer to the center. Other stars will gain that energy and get thrown out into higher orbits or completely out of the globular cluster. So over time, it gets smaller and smaller and compresses down. The stars compress down to a smaller space. So we're going to look at one in just a bit. Yeah, here we go. Messier 71. Yeah, that'll do. So going from this guy, I'm going to save him, because why not? Yeah, from these guys here, we're going to stop this. Stop. There we go. We're going to slew to Messier 71. That's close to where I want to be. Messier 71. Okay. Confirm slew. There we go. Now it's going. Let's change our time 15 seconds to 2 seconds. This is, I want to get to a good point. And not enough stars. Okay, got this guy. Let's see what this looks like. Okay, I don't see it. Let's figure out how far off we are. Solution found. It is just over half a degree off. Okay. I don't see anything. So what we have to do is give it a longer exposure. So 15 seconds as well. See what happens. Should be somewhere here in the middle. Should be. Got to check the other one. Okay. There we go. This is not the nicest example of one, but if we do some live stacking, deep skies, do this again, hopefully we'll pick up some more data. Starting a new stack. Excellent. Okay, first one. There we go. So it's not really visible. This is not the best one. Oh yeah, that's definitely not the best one. Where is Hercules? Is Hercules up yet? Not yet. Oh wait, here's Pegasus, but not Hercules. Let's see. Trying to find. Let's see. Messier 13. M13. Where is it? Where is it? It is. Ooh, no. It is far in the northwest sky. It is very, very low. Yeah, there's no point in grabbing it. But this is a globular. It's just not a great one. It's hard to tell. But I need a lot more aperture because there are a lot more stars there. Yeah, there's a lot more stars, but it extends out quite a bit. It just doesn't have that well of a defined core at this aperture. All right. There we are. Okay, if you have any questions or comments, you always put them in the chat. Almost 11 p.m. here in Texas. So I've been doing this for 2.5 hours, roughly. Okay. No. This is what I'm getting with the big scope. We just have too much wind. Just have way too much wind. Super annoying because I really wanted to dig into Saturn. This telescope is really, really good at let's see, where's my plate solve? Yeah, it's all fine. Those settings are fine. It's just too much wind. So the stars are moving in all sorts of directions. I can't get a decent long exposure. Yeah, I can't. It's so annoying. So annoying. But this one works fine because it is a much smaller telescope. Got a picture of it somewhere. Let's see. Let's see, actually, if I can find a picture of it somewhere. Let's see. Yeah, there we go. Oops. Yeah, this is the telescope. Oops. Not in this mount. I have a different mount for it. But this is a telescope. It's a small refractor. It's not very big at all. It doesn't need to be. It's a wide angle scope. I have a little guide scope on top, a little focuser, and then the astronomical camera on the back. It is meant as a wide field instrument, so it takes wide field images. It's all that it does. It's quite good at it, but that's all that it does. But it's small, and because it's small and it's on a nice steady mount, it does not need a big mount, and even with wind, it's going to be pretty stable. These stars are still pretty round. So I'm happy with this one. I'm glad I put this one on. Gives us a backup, because otherwise we'd be out of luck. We'd be looking at something like this. These appear to be nice round stars at the moment. Let's see if we can plate solve this one. I just need this thing to tell me what we're looking at. It's supposed to be Saturn here somewhere. I don't think it's finding it. Plate solve settings. I'm going to switch it. Yeah. Okay. I'm going to try this again. Use the built-in plate solver. There. Okay. Well, there we are then. Let's see if we can get something. Let's bump it up here. Saturn. The slew. Okay. There we go. Oh, finally. Okay. All right. 8 seconds. Way too long of an exposure. 1/8 of a second's what we want. There we go. All right. Oh, come on. Please. It's gonna do it again, isn't it? It's not what I wanted. Okay. I'm going to close it, reconnect to it. I think I'm going to have to hardwire everything. Right now it's going over a, it does go over a wireless connection at one point, but yeah, I'm going to have to. There we are. Okay. Nope. Nope. There we go. We have a Saturn. Okay, raw 16. Drop this way down. Yeah, let's bring this back up to. Okay. All right. There we go. Let's do zoom. I'm trying to be super careful so it doesn't crash out. Okay. I'm going to get this even smaller. Yeah. Okay. Cool. I'm getting a lot more frames a second for this thing. Let's see if we can get this thing running. Okay, so Anyone new joining us, we're looking at Saturn, and I just have to get my settings right. Okay, because the rings are very, very thin. They're really hard to see. I have to really bump them up like this to get anything. This is Titan. This is Rhea. And Tethys was somewhere over here. Let me see if I can find it again. There's Saturn. Okay. Is that Tethys? Yes. Yep. This is Tethys over here. Titan and Rhea. And Dion is actually, it's no longer in front of the sun, but it is so close, it is within the rings to the point where we're not going to be able to find it. Dion is over here. It was right there when we started. 2 hours later, it's now over here. But it is in the rings. And see, if I start changing the gain, I'm not picking anything up. But we are definitely seeing Titan, Rhea, and Tethys, moons of Saturn. Oops. Come on. Please don't. There we go. So here's Saturn. It's windy. That's why it's moving around. And if I drop it down, let's do this actually. What if I can do this? What if I can do this? I can do that. No. And do this. And I'm playing around right now. I'm trying to figure out the best thing that I can do to bring anything up. See, a little bit of banding. So let's do this. Tools, and we're going to do planetary stacking. Yes. Okay, I want to bring this way up. This down. Okay. Okay. Yep. I'm not really getting a whole lot. Stabilization, alignment, surface, planet, full disk, stacking mode, multi-point. Okay. Frame filtering, we're just taking some of the best ones. We're dumping out all the bad, ugly frames because I don't want them. Oops. Okay, we're getting that. I'm going to drop down gain again. See if this will help or if it will hurt. Reset the stack. There we go. What I'm trying to do is see if we can find any banding. I don't see any right now. Yeah, we're getting a little bit. I think I just need a lot more data. And it's just so windy. It's just windy. The atmosphere is not very stable. So we're just not going to get good results with this, unfortunately. But we do have Saturn. Oops. Log back in. Okay. We've got Saturn. We can see rings. And if I push it a little bit more, we have Titan. If I push it even more. Come on. Here we go. If I push it even more, we can see Rhea. And then we see Tethys. So, Titan, this is the moon of Saturn that has a thick methane atmosphere. Methane-ethane atmosphere. Rhea. And we have Tethys. Then the rings of Saturn right now are pretty close to edge on. So we're barely seeing. Now, the interesting thing about the rings themselves are not very thick, as in the thickness of them. They're very wide, but not very thick. In fact, we think that the thickness is about 10 meters. So in places 30 something feet, maybe 40 feet. It is not very much at all. But they're made of ice and they're quite bright, so fairly easily visible. Just thin. I'm going to get a little bit sharper. Reset the stack. You know what? I gotta turn off the stack now. So we're gonna zoom in a little bit more. Kicks and grins. I want to see if this is actually a focusing issue or something else. It's getting better or worse. I'm gonna play optometrist. Better or worse? Such a small change, it's hard to tell. Let's go negative 100. Probably worse. Oy. That may be better. That may be better. I don't know if you can tell. I can see a little bit of banding through here. So let's see. Let's see what we can see. Yeah, it's hard to tell. Yep, just hard to tell. I don't think it's a good night for seeing. So, but we saw Saturn, very, very thin rings. And we saw 3 of its moons. So yeah, you can see a little bit of banding. Not very much, but it is there. Very thin rings. Yep. Okay. So I'm kind of done with Saturn. Oops. I'm going to jump on to Neptune. Because why not? Saturn, Jupiter, Neptune. There we go, Neptune. We're not going to spend a whole lot of time on it just because $200, come on. Neptune. And let's make this really small. Even smaller. Come on. There we go. Oop, too small. No, I'm missing it. Yep, this is the fun part of astrophotography, is messing with it till you get it right. Let's see where I lost it. Sounds like meantime, Globular's coming in a little bit better. I'm gonna brighter. There we go, a little bit brighter, so we can see a little bit more of it down in the middle. Yep. Okay. Let's leave that one as it is and go back. There's Neptune. Okay. I'm going to try if this lets me. Then we need a faster connection. Yep. Even hardwired, it's just not fast enough. Okay. Yep, let's restart it. Once more. Okay. Tools, and I'm going to do the planetary stacking again. You can see it's just windy. The streaking pattern, this motion, it's just wind. It's just not very, very good. I'm not happy with it at all. So I'm looking for something else that I can do. Let's see tonight. I've got it on my phone here. Phobos, Jupiter. Ooh. Bright moon near Saturn. Jupiter rises at 1:13 in the morning, so that's not going to work. Same thing, Uranus rises soon, but it's still pretty low. Titan, Andromeda, Messier 2. Where's Messier 2? Rise to 16, so that's 4. Okay. Let's check out Messier 2 then. That's another. No, you know what? I don't want that. I want Helix. Helix? Messier 20. Messier 77. No. Trying to find something nice that's easily visible. And is this too low? No? Well, maybe. Maybe. 7293. Maybe. 7293. Confirm slew. Let's let it move over. Clear the stack. All right. That does what it's going to do. Yep, not happy with this at all. There's just too much wind. It happens. It's not a great night for viewing. I'm going to jump back on the moon so you can see what I mean. Solar system. Moon. Confirm the slew. And we're going to... Oops. Oh, yeah. I'm wondering if it is a bandwidth issue that I just don't have enough bandwidth going out to the laptops outside. I may have to hardwire everything. Not looking forward to that. But it may be necessary. Ugh. Yep. All right, let's see what this guy does. Oops. Okay, here we go. What are we looking at? Okay, something in brown. This is low in the sky. It's ugly. Stop that. All right, take an image, find these stars, figure out what we are pointed at. Okay, we're very, very close. Cool. Lead offset. There we go. So we have the helix right there. We have a 15-second. Yep, oops. 15 seconds, that's fine. So we can do tools and deep sky stacking. Let's go ahead, just let it stack. Then it will start cleaning that up, hopefully with some good data. I'm still trying to get this thing. Yeah. Uh-oh. Well, that's not right. Let's try it again. Clear the stack. Ugh. Huh. Okay, yeah, brown something. I think it's still, yeah, it's close to, it's not that far off from the moon. Oh yeah, it's very close to the moon. All right, I don't think we can do the helix. The helix is way too close to the moon. North American? I have to do North American. Yeah, all this stuff here, this is just glow from the moon. So we're not going to see this very well, but just for kicks and grins, let's zoom in and see what it looks like. That. I can't really enhance it anymore. Maybe. Oh, it's so ugly. Yeah, that's just, I can't. Yeah. Being where it is. Yeah. I know where it should be. It is right there, but it's so close to the moon that we can't see anything. There's not a point in doing this, not for this one. Let's pick something well off of the moon. NGC 7000. This is a North American nebula. Hopefully this will look a bit prettier. All right. Should be streaky stars. Not yet. There's a streak of something. Okay, let's let it settle. Next image. There we go. Okay, now we do a plate solve. So plate solve again, it takes an image of the sky, figures out what it's pointing at, and realizes, oh, it's not quite where you should be. So it fixes that. Next image, the stars have moved just a tiny little bit. Just that much. And the next one should be good. There we are. And now we can do live stacking deep sky. But I need a little bit more. I need 30-second exposures. And the reason why I'm doing a 30-second exposure is the North American Nebula is it's rather dim. Let me see if I can bring up one of mine of the North American. Let's see. Nope. When did I last take North American? There we go. So there we go. North American Nebula. Mexico, Florida, North America, United States-ish, Canada. It's called North American Nebula because it kind of looks like, well, like North America from a particular point of view. Here we go. So this is my image of it, and I can make it a bit smaller. You can kind of see This is called the Cygnus Wall through here. This is a dark nebula. This is not the best of images, but it's halfway decent. This is a dark nebula where you see all of these stars here, and this is nebula that's deep in the Milky Way. All these stars, stars on top of stars on top of stars on top of stars. And then you get to a region like this where you don't have very many. Well, what happened? The stars disappeared? Stars there? Well, no, there are lots of stars, but there's a region of dark dust which is blocking our view. And you can see that through here. There's these dark bands of dust, and where it's not as thick, you can see the background stars come through in this whole area. But this region of dust is just blocking out that light. Now, all through here, the reddish color comes from hydrogen light, or hydrogen. Hydrogen is excited by large blue stars throwing off a lot of ultraviolet radiation. The ultraviolet photons hit the electrons in the hydrogen atom, excite them to a higher energy level, and then when they drop back down, they let off a single photon of a very, very particular wavelength of red light. And we call that hydrogen alpha light, because that's the light that hydrogen gives off at that particular energy level. That's the wavelength. So by looking for this particular color, we know where hydrogen exists in the galaxy and in other galaxies. We're looking at where it's excited. Now, if there's hydrogen gas out in deep space, not near any stars, it may be mixed up with dust. It may look like this. It doesn't glow. It may be transparent. It may look like dust. It may be thick enough to block out some of that light. But we wouldn't be able to tell. We can only see things if they're glowing, if they're giving off their own light. So the dust in here, we can't see the dust. But by using an infrared camera, we can pierce the dust. So we can look at things like the Horsehead Nebula and see the stars behind it using the James Webb Telescope, because that is an infrared scope. So this is my version. And over here, we have the live version. Let's see if it looks any better. Here we go. So here's a Cygnus wall. So I bring this over here. This is kind of, this is rotated 90 degrees counterclockwise. Or no, clockwise, sorry. This is rotated 90 degrees clockwise. So this feature here is this feature down here. That feature there is right there. This area here is our dust band. You can see this dust lane right through here, which corresponds to this one here. So, is that visible? Yeah, I'm not sure what's up with the other one. I just don't know. It's like it's too much wind, but it's... I'm losing my connection to that machine, to the other laptop. I am glad I set this one up as my backup, just in case. Let's see if I can fix. Oh, here we go. That'll do. No wonder. Okay, one moment. There we are. Okay. So this is processing nicely. It'll get there eventually. There we go. Now we have some red in it. We've messed with the background. It looks reddish the way it should be. It looks closer to this. Just rotated a bit. And that's not too bad. It's not too bad at all. It is getting there. We've stacked 12 so far. Let's go ahead and zoom in 100%. Yeah, it's still noisy, but it's not bad for a full moon. We have nice round stars, and I'm not even doing any tracking. I have not started or any auto guiding. Uh-oh. Green pixels. Means we have dead pixels on the chip. It happens. We process them out during post-production. It happens. We'll see green ones, red ones, and blue ones. It just means that, they're just bad pixels. Usually it's the red and blue ones that go out, so that all that's left is green, but we see blue one right there, red one right there, red one. Yeah, it just happens. So we actually make bad pixel maps. Okay, well. That's why we're not looking at the moon. It's because the wind is really shaking it about. It's fine the last couple days, not fine today. So if I zoom in, it doesn't look that bad. Doesn't look that bad, but at the same time, yeah, it's shaking a lot. So go back to Sea of Tranquility, Ritter, and Sabine, and we have was it Mulcahy? Was it Mulcahy? And the Apollo 11 landing site. I gotta keep moving the mouse around. Just past that little blob there, right over here. So, yeah, this is why we're not looking at the moon, because it's just too shaky. I had hoped to actually do some imaging. I wanted to try to catch a comet tonight. It's not going to happen. I'm just glad I was able to get one scope connected and do at least a little bit of imaging on something that's not moving around nearly as much. Let's see. So it is now 11:30 almost. It is getting late. I'm getting tired. I'm going to have to go outside and shut everything down and cover it before I go to bed. We can do one more object. If anyone has any suggestions, anyone has any ideas, just throw them out. Got 19 frames stacked on this thing. It's not looking too bad at all. It is entirely feasible. I have to do some post-processing, get some dark zones on that, get it looking okay, but it's not bad. Oh, excuse me. Let's see. I am looking around there. Now the ring nebula is going to be really tiny. I thought about that. It's just I wanted to grab the ring nebula with the bigger scope. It's just so tiny that it will shake around. We're not going to be able to see anything with it. Hercules cluster, that's slow in this. Oh, that's no, not feasible. That's going to be way too low. Yeah, if you have any ideas, please toss them out. Nope, blue snowball. We're not doing the blue snowball. All that stuff is too small. Triangulum, it's not going to be feasible here. California Nebula, too low in the sky. Hades cluster Pleiades. We can do Pleiades. Oh, it's right next to... How is the Pleiades so close to the moon? What? Now. Uranus. What? No. Now I have to figure out what's going on with my application here. Now. The moon is still... Okay, let's do Pleiades. I think it's going to be... No, it's just going to be too close to the moon. I'm trying to figure out what is going on because this is not right. This is not right. How can this be right? It's not showing the moon in the right place. Yeah. Something about my application is not working. I'm using Sky Safari on the phone. It is not showing up where it should be. There we go. Now I can see where the moon is. Okay. Now we can do... Yeah, now we can do Pleiades. Okay. So we've got 24 images out of this thing. That's not too bad. This is amp glow. I can process this out without much of an issue. But we can see North American Nebula. So this is a processed version. And then this is the raw stacked version, I guess you can call it. Got any questions? Questions, comments? Want to see something in specific, let me know. Otherwise, we'll jump on to Pleiades, which is really low in the sky, and hopefully it's above my tree line. I hope it's above my tree line. We shall see. All right. Let's stop with this. Okay, and we'll move to Pleiades. Pleiades is Messier 45. Confirm that slew. Grab that. Instead of the 30-second one, we will do 2 seconds because I want to be able to find it fairly quickly. There we go. Just Pleiades. And how far off are we? 0.61 degrees, not very much. Cool. Okay. Pleiades. So let's see what we can see. Okay, I'm going to set this as another 30-second exposure. And the Pleiades is one of these open clusters. And the Pleiades was formed somewhere far away, and it looks like it's all together, but in reality, what we're seeing it is deep. So there's some that's closer to us, some that's further away, and they're spreading out in this direction, but they're moving through a region of dust. So it's very, very dusty there. When we see first frame, okay? There we go. So the Seven Sisters, or Subaru in Japanese, yes, that's where the car gets its name from. And if you look at the logo of a Subaru, it is the Seven Sisters. So we're going to let it start stacking, let it process. Okay, and it will get nicer and nicer. In the meantime, what do I want to look at? I was going to check something. There we go. I was going to check if I have Pleiades somewhere, a processed version. I may. I don't remember. I may. Let's see. There's North American. There we go. So this is the same orientation? No. No, this is flipped. So I have it flipped in this one to the right way. This one should be flipped as well. Flipped horizontally. So you can see this trail of stars here. There's this trail of stars here. 1, 2, 1, 2, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So you can see just how dusty this whole region is. And it's just dust. And the reason why it's blue is it's being lit up by these stars. This is what we call a reflection nebula. So we typically have 3 different types of nebula. We have emission nebula. Emission nebula is composed of really elemental gases, so hydrogen, sulfur, oxygen, can have some carbon in places, but those are the 3 that we typically look at. So hydrogen is red, sulfur is also red, but it's a slightly different wavelength of red. So we can actually make filters that block out all light except for this narrow slice of hydrogen light or this narrow slice of sulfur light, but they're 2 separate ones. We can have 2 filters, or we can have 1 filter which overlaps both. There's a whole lot of options you can do. And then there's oxygen. So oxygen is a blue-green color. And we'll see that in some nebula. It's like it'll be greenish blue. You can see that in the Orion Nebula. You see that in planetary nebula like the Helix and the Ring. But this is blue. This is a blue one, not red, not greenish blue. It is blue because these are big, bright blue stars. And what we're seeing here is just dust. The light from the stars is reflecting off of the dust. It's reflecting the same color that's coming off of the stars. So if they were red stars, you would see red, like reddish glow coming from the dust. If it was a yellow star, you would see yellow. And now that I think about it, I do have an example of that. So while we're waiting for this, let me grab the other one that I've got. Let's see. Where'd it go? I had it here somewhere. Somewhere. Yeah, I don't want to use that one. Let's do this. There we go. Okay. Let me in. Knock, knock. Okay. All right, here we go. Yeah, here we are. That is a really good example. Cool. Okay. While we're waiting for this thing to get dusty, you can start seeing a little bit around here. We'll match it up in a minute. But when I was saying that we have reflection nebula. Oh, this is actually a really good one. Okay, here's what I'm going to look at. There we go. The Rho Ophiuchi Cloud Complex. This is one of my images. Yeah, this was from a rented telescope. This was a panel. So this was multiple images that the images needed to be stacked, and then the images needed to be stitched together because it was a 2x3 panel. So it was 2 images across, 3 down. And the neat thing about this is I can actually, this does a plate solve as well, so it'll tell me, hey, what are these stars, what are these different objects? So I'm going to do it this way. Oh, excuse me. So what are we looking at? We are looking at the Rho Ophiuchi region on the border of Ophiuchus and Antares. What we see here is Antares, a big yellow star, yellow supergiant, and it is glowing and it is lighting up the dust in its region. So all this is yellow from Antares. This is a globular cluster. There we go. All right, so it'll take a minute. This is a globular cluster. This is Messier 4. And this thing is located, well, let's do this. Rho Ophiuchi is just off of the Milky Way, but it is much closer than the center of the Milky Way to us. Messier 4 is located through the Milky Way and out the other side. So this is fairly large, but it looks small only because it's so distant. We have these red emission nebula. Still going? There we go. So let's look at Antares. I made this a very, very high resolution image. Ooh, Antares, and it's glowing all through here. We go over to this area. Let's see. And we have red emission nebula. So this is hydrogen gas that's glowing. And when we go up, we have dusty nebula. So this is just dust. It's blocking out the light from behind, and it's maybe a little bit lit up. So it's just dust. We have dark nebula. These bands here, which is dust that is blocking the light from behind. We have more reflection nebula all through here. And let's see what else. More dust. You can see this is so dark, it's blocking out all the light from the stars behind. These stars that are coming through, they're actually in front of the dark nebula. More dark nebula. This actually extends out to the core of the Milky Way. But apparently, it doesn't actually, it just extends out in that general direction. Then back down to Antares. So you can see we have a bunch of different types of nebula and different types of reflectivity. I just don't see any oxygen here. Rho Ophiuchi is actually this star complex here. It's I can't remember, it's like, is it 7 or 8 stars? Yeah, it's like 7 or 8 stars, and some of them are large blue giants, which is why this whole area is lit up blue. Then you can also see there's some red through here, so that is hydrogen that's being excited by the ultraviolet light. So yeah, that's fun. Okay, so what do we have here? It is still going. We've got 20. So let's see. Let's see if I just do it this way. What do I get? Not that much. Yeah, we'll also see some velocity though. So let's zoom in. Yep. It's not easy to see, but there is a glow. And I wonder if I can manage this. No. No. Just slightly. You can see this, there's an... Yeah. Okay, fine. So I can get back to where we were. Okay. There we go. Now we can see some of the dustiness here, some of the dustiness around the stars there. This is amp glow, that's not it. It's not that great of a night, but you can begin to see this dustiness. So this is 11 minutes of exposure. It's not half bad. The noise levels drop down quite a bit, but it doesn't look as good as, as this, only because this one was taken at dark sky site. It was taken for, there were much longer exposures. I think it was about 5-minute exposures, and a lot of processing. Um, but we can see right now, just right now, this area here, this area here. We can see this dustiness just starting to appear. Then the dustiness around that star is all this over here. And we can see this line here, where it's darker and then lighter. Here we go. These lines through here, where it's darker. That's this line here and darker. It just flipped. So, all right. So the dust. So Bart has a comment that the dust is a fluorescence is like a blacklight poster would under a blacklight. Yes, it is actually fluorescing. The gases, the hydrogen, the sulfur, and the oxygen, they are actually fluorescing. Here, it is just reflecting. There's no, there's not really a change in energy levels of any gases. This is light reflecting off of dust bands. And in this case, the cluster, the Pleiades cluster, is moving through just a dusty area of the galaxy. And if it wasn't for the fact that these bright stars were in it, we wouldn't even see it. We would just see it as like a darker spot in the general galaxy, and we wouldn't be able to see the stars behind it. But it's not in the Milky Way, so it'd be hard to see. But just the fact that these stars are moving through this area, they're lighting up all this dust for us. So Yoki, let's see. Oh, here's a, okay, now we can do that. So talk about the globular clusters. Here we go. Close that one down. So this is a globular cluster. This is 47 Tucanae. This is in the Toucan in the southern hemisphere. This is off of a rented scope. And this is what a globular looks like. This is a rather large globular. You can see that it's got a very, very well-defined core. It's not spread out. This is not an open cluster. This is a globular. It looks like a big ball. When you see these through a telescope, they look like fuzzy balls. That's not how I describe them. When you have enough magnification that you can take a really, really good look at them, if you can resolve the stars down to the core, that's going to be a pretty good telescope. It's not just a blob down there. The outer ones, these are still usually a part of the cluster. Some of them are already traveling out and they're leaving the cluster. But as they do, more fall into the center. So there's not a black hole here. This is not a galaxy. It's not like a galaxy. It is just a group of stars. They're really old stars. There are some that have planetary nebula in them from when stars died. But they're orbiting a common, we call it a barycenter. They're orbiting a common center of gravity. But it's like the average of the gravity of all the stars in the cluster and calculated by their distance. So it's a point in space, not a actual physical object there. So it's not a black hole, it's not a singularity, it's nothing like that. But this is what we tried to see. Conditions are not great for seeing it now. That's okay. This was the Mars occultation that we had 9 months ago already. Okay. So, yep. And this is something that I will be doing hopefully in the next week. I did some solar imaging on Thursday. This is just one frame. So we have sunspots and we have some prominences. Let's see, there's a prominence there. Around the edge, there's a small one. Oops. There's one right there. I think another one down here. It's a little jet. But this one was the big one coming off. We'll see what the data is like. What I'm going to be trying to do is another time lapse. So I think I have about 7 hours, 8 hours. So that's maybe 7, almost 8 hours worth of data. I don't know exactly. I'll have to double check. But it is still processing. I'm still working on the data. That's all I can say is I'm still processing it. I haven't even gotten to the point where I have images like this. This is a one-off image that I did. But once I get it done, then I will go ahead and put this up as another movie on the YouTube channel. So if you want to see what that's like, please check out some of the other videos on the channel. I have, there's one, it's a 3-hour time lapse of the sun. This was taken May 2 years ago, I think it was. Yeah, I think it's about 2 years old now. So you'll be able to see kind of the solar activity. You'll be able to see some prominences. You'll be able to see some explosions off of the surface of the sun. It's really neat. It doesn't take that much time to watch. I have a longer version of it as well, go into more detail. And we are seeing some of the dustiness come out now. So, yep. No, it was better. It was better. Yeah, you can see there's a lot of light pollution. We have to get rid of a lot of. There's just more processing that needs to be done, and it's not something that you can really do on the fly. It takes some time. The computer's got to crunch numbers, so it is what it is. Okay, wow, it is almost midnight now, so I'm gonna jump on the other machine, see what it's like. Okay, so we'll have one more view of the moon. Let's see. Let's see if it'll do this right. Nope. It is never, ever, ever the button that you want to press. Never. It's always going to be something else. So here we go. One more look at the moon. See how much it moves. Yeah, still moving. So, not the greatest night to do lunar astrophotography, but let's do a quick overview again. We're looking at Copernicus right now. You can see the central rebound mountain. And let's see if we can do this. Here we go. So let's do it this way. Here we go. Look at Copernicus right over here. That big guy. So blasting out all those rays. Okay, out. Fit. Okay, so down here we have Tycho. Let's look at Tycho again. Go down, and here's Tycho. You can see the central rebound mountain right there in the middle. And go north to Plato. Here's Plato right over here. Real big, real pretty. Then out, no direction. Sea of Tranquility. Right over here is the Apollo 11 landing site. And I need to go to this direction. Yes. I wanted to go. Here we go. Okay. Earlier we were looking at, what were we looking at? We were looking at, not Plato. Over here, we were looking at Pythagoras. That's it. All right. let's go find Pythagoras again. So sinus iridium. There's Pythagoras out there. Cool. Cool. All right. Yeah, that's what I want. Okay. So we're going to go. It's dark because this is morning. Pythagoras is somewhere over here. There we go. There's Pythagoras. Okay. All right. What did we do last time? There we go. It's been a couple of hours, but we can always go back to the video. Pythagoras, that central peak, looks a little bit brighter. I swear it's got some more pixels on it than it did earlier. The wind. Yeah, I'm just gonna have to cover everything up. But look at that. Now you can tell. You can actually tell it's not just a couple of pixels. It's a triangle. It's a mountain. It's a mountain, at least one mountain, right in the middle. So we're looking across here, sinus iridium, all the way over to Pythagoras, because this is the only thing. And that's what we're seeing. There we go. Just stop moving. I swear, just that mountain right there, we're just seeing the very tip of it lit up by the morning sun on the moon. Okay. It is almost midnight. Been doing this now for 3.5 hours. My legs are tired. I actually sprained my foot a month and not quite 2 months ago. And I just can't keep standing on it all night long as much as I would like to. So I'm going to go ahead and sign off. Thank you very much for joining us. And hopefully we'll be able to do something like this fairly soon again. Morning on the moon, huh? Okay, again, my name is Chris Mornitsky. This has been a presentation of the Fort Worth Astronomical Society. Please like and subscribe. It helps the algorithm. And hopefully I'll have some new videos coming out real soon. Thank you very much, and good night.